December 7th. In 41, Pearl Harbor was engulfed in flames, and within 72 hours, the United States military faced a logistical nightmare that had nothing to do with battleships or aircraft. Across the Pacific Theater, from the Philippines to Wake Island, American soldiers were sleeping in rotting canvas tents, soaked through by weeks of tropical rain. Morning briefings at the War Department turned grim as field reports arrived describing flooded supply depots, ruined ammunition, and soldiers hospitalized with pneumonia after their shelters were destroyed by the monsoon season. Traditional wooden barracks required skilled carpenters, weeks of construction, and a steady supply of timber resources that were impossible to find on remote coral islands. The Navy calculated that it would take 18 months to build enough conventional housing for the troops that needed to be deployed immediately. In Washington, Brigadier General Eugene Rybold stood before a crisis table covered with weather charts and construction schedules. His engineers presented him with an impossible equation. They needed a building that could be manufactured in Pennsylvania, shipped 10,000 miles through submarine-infested waters, assembled by exhausted Marines who had never held a wrench, and withstand everything the Pacific could throw at it, 130-degree Fahrenheit heat. Category 5 storms. Monsoon rains dumping 15 inches in 6 hours, and even the threat of Japanese bombing. A standard Army tent cost $12, but lasted barely a month in the jungle. A wooden barracks cost $8,000 and required a construction crew for 6 weeks. Neither option worked when you were moving across Pacific Islands and needed shelter for 50,000 men almost overnight. The British had fought longer and offered a clue from their experience in North Africa. Since 1916, they had used the Nissen hut, a half-cylinder steel shelter invented by Canadian engineer Peter Nissen during World War I. These corrugated metal huts could house 30 soldiers, needed no skilled labor to build, and resisted desert sandstorms. But the Nissen design had serious flaws when used in the Pacific. The British version relied on heavy steel panels that required cranes for lifting. Its ventilation system worked well in the Libyan desert, but turned the inside into an oven in the humid air of the Philippines. The greatest drawback was that each hut required a custom foundation, either poured concrete or wooden platforms, which brought the carpentry problem right back. Rybold's team calculated that they needed shelter for 2 million service members across hundreds of islands and bases. The math was devastating. At the normal pace of construction, the war would be over before even half the troops had a roof over their heads. Soldiers wrote home describing how they woke to find their boots filled with rainwater, how mold grew overnight on their uniforms, and how temporary tents collapsed in storms, forcing men to crawl through mud at 3 in the morning. Army Medical Corps reports showed that respiratory infections were sending more men to hospitals than enemy fire in some regions. This was no longer about comfort. It was about keeping the fighting force alive long enough to reach the front lines. The call went out to American engineering firms, university research departments, and Navy construction battalions. The design brief sounded almost like science fiction: create a building lighter than a Jeep, small enough to fit on a rail car, requiring no foundation, capable of assembly in a single day using basic tools, costing less than $1,000, and strong enough to endure conditions that could destroy permanent structures. Oh, and 10,000 units had to be ready for shipment within 6 months. In February 1942, a group of engineers in Rhode Island was about to turn an architectural impossibility into reality. The blueprint for the British Nissen hut arrived at the Navy's Bureau of Yards and Docks in what became an unusual wartime collaboration. Grateful for America's supply shipments, British engineers shared their detailed technical drawings of their World War I-era shelters. These were semicircular tunnels, 16 feet wide, made from corrugated steel sheets bolted to wooden frames. Commander John Philip Drosfeld studied the specifications, and immediately saw both the brilliance and the flaws. The brilliance lay in the dome-shaped design, which naturally deflected wind and drained rainwater without complex engineering. The flaws, however, were numerous and serious under Pacific conditions. The British huts weighed 3 tons when disassembled, required foundation bolts drilled into concrete, and contained interior wooden framing, a perfect feast for termites in tropical climates. Drosfeld circled the ventilation notes in red ink. 2 small windows designed for Scottish weather would turn these huts into ovens under the 98-degree Fahrenheit heat of Guadalcanal. Yet there was another American voice in this conversation, coming from an unexpected direction. Buckminster Fuller had been promoting the idea of prefabricated homes since the 1920s. Though most architects dismissed him as eccentric, his Dymaxion house concept factory-built, lightweight, and assembled on-site sounded almost prophetic. By 1942, Fuller's vision of mass-producing housing like automobiles, using industrial materials instead of traditional wood, and designing for rapid deployment seemed far less radical when your nation needed to build an entire city of shelters every month. The military had not directly consulted Fuller, but his published writings circulated through engineering departments, and his central philosophy proved invaluable. Treat buildings as manufactured products, not construction projects. The Navy embraced this thinking at its base in Quonset Point, Rhode Island, a newly established air station on Narragansett Bay. The location was no accident. Rhode Island had deep expertise in sheet metal manufacturing from its jewelry and silverware industries, proximity to Pennsylvania's steel mills, and shipyards skilled in marine-grade corrosion resistance. By March 1942, the Navy had assembled an unusual team of structural engineers from the Strand Steel Corporation, known for their prefabricated farm buildings, architects from the George A. Fuller Construction Company, specialists in rapid assembly methods, and Navy officers who had actually served in the Pacific and knew firsthand what stormproof really meant beyond what was written in manuals. The team's leader, Otto Brandenberger, brought with him a background in agricultural construction that turned out to be the perfect match for the challenge. His Strand steel barns used self-supporting curved panels. They required no internal framing, which meant no wood for termites and no complex joints to fail during storms. Brandenberger's bold proposal was to remove the wooden skeleton of the Nissen hut entirely and let the corrugated steel shell bear the full structural load. This went against conventional architectural wisdom in 1942, when steel was reserved for bridges and skyscrapers, not self-supporting buildings. But Brandenberger knew his barns had already survived Midwest tornadoes without internal framing, and he was confident the same principle could be scaled up to meet the needs of a global war. The British contributed another crucial element through their hard-earned experience. Their Nissen huts in Burma and Singapore had shown them exactly how tropical environments could destroy buildings. Mold was not just cosmetic. It ate away at wood preservatives and paint within months. Humidity did not simply make things damp. It corroded metal fasteners until roofs collapsed. Insects were not just a nuisance. Carpenter ants could hollow out wooden support beams in a single season. British reports read like horror stories, but they gave the Quonset team a checklist of everything that had to be engineered out from day one. No wood in contact with the ground. All steel hot-dip galvanized rather than just painted, and ventilation strong enough to prevent condensation. Every bolt had to be reachable for replacement without dismantling the structure. By April 1942, a hybrid vision had taken shape. It combined the elegant arch of the Nissen hut, removed everything that made it heavy or fragile, added Fuller's philosophy of mass production and the power of American steel manufacturing, and refined every detail for the harsh realities of the Pacific Island War. On April 15th, Chapter 1942. Otto Brandenberger walked into a warehouse at Quonset Point with 30 engineers and a deadline that would have seemed absurd if not for the urgency of war 60 days to design, prototype, test, and approve an entirely new building system that had never existed before. The team worked around the clock in shifts, sleeping on folding cots lined against the warehouse walls, surviving on Navy mess hall coffee and the pressure to either succeed brilliantly or fail completely. Brandenberger divided his crew into specialist groups. One handled aerodynamics and structural loads. Another focused on how to nest components for efficient shipping. A third tackled the persistent challenge of joints and fasteners that had troubled the British design. The first radical decision came on day 3. Traditional architectural blueprints took weeks to complete. And the team did not have weeks. Instead, they built in real-time sketching details in the morning, having the metal shop fabricate them by afternoon, testing overnight, and revising at dawn. This iterative prototyping method is standard today in 2020. But in 1942, it was revolutionary when buildings were still designed entirely on paper before a single part was cut. The warehouse floor became a laboratory littered with failed joint experiments, bent test panels, and progressively refined versions of each component. The engineers borrowed a technique from the aircraft industry. Every part was numbered, every revision documented, and nothing advanced to the next prototype until the previous model's weaknesses had been fully resolved. The dimensions came from harsh practicality rather than aesthetics. 16 feet wide, the maximum that fit on a standard railcar without special permits. Each section was 20 feet long, short enough for 4 men to lift a panel, but long enough to create usable interior space. Fully assembled. It stretched 48 feet, capable of housing 36 men in bunk beds or being converted into an office, medical station, or supply depot. The Quonset team discovered that this size hit a perfect balance in structural engineering. Make it smaller, and transport capacity was wasted. Make it larger, and the panels became too heavy for field assembly. Or the arch required internal supports, bringing back all the problems they were trying to eliminate. Calculating the radius of the arch consumed 2 full weeks of their 60-day deadline. Too shallow, and wind could peel off the structure like a sardine can. Too steep, and valuable interior space would be lost, while the end walls would become more complex to design. Brandenberger's team settled on an 8-foot radius, a perfect semicircle providing 7 feet of headroom at the sides and creating what structural engineers call a self-bracing arch. Corrugated steel naturally wanted to hold this curve, which meant the panels could be thinner and lighter than flat sheets of the same strength. Load calculations showed that, in theory, this design could withstand snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. But theory and the Pacific storms were 2 entirely different challenges. By the 40th day, the team had something that finally looked workable. A kind of Frankenstein creation with riveted panels, experimental joints, and borrowed hardware. The first complete prototype was assembled on May 25th, 1942, by 6 Navy sailors who received only 4 hours of instruction and a set of basic hand tools. The total assembly time was 14 hours, a promising figure, but still not good enough. The Navy wanted a structure that could be built in a single day because the Marine Corps' landing schedules left no room for lengthy construction projects. The team quickly identified the bottleneck: the flooring system. They had originally included a wooden floor in the design, but it proved to be the slowest component to assemble and the first to rot in tropical climates. The solution was simple yet ingenious: remove the floor entirely from the basic design. The hut could be set directly on whatever surface was available: coral, sand, soil, or, if lucky, gravel. for installations that required a finished floor. One could be added later as a separate project. But the core shelter remained fully weather-resistant without it. This single decision cut the assembly time down to 8 hours and reduced shipping weight by 200 pounds per unit. On June 10th, Chapter 42, the final prototype was completed. It consisted of 96 corrugated steel panels, each weighing less than 50 pounds, fitted together to create 720 square feet of enclosed space. The total material cost was $394, and the total weight was 9,000 pounds. The real test began when the prototype Quonset faced a technical trial as rigorous as an interrogation. The Navy's structural engineers arrived with wind load charts, storm data from weather stations across the Pacific, and a healthy skepticism that this corrugated tunnel could withstand what nature routinely threw at tropical islands. The numbers they worked with were not theoretical. They came from real storms. Typhoon Gloria had struck Guam in November 1940 with sustained winds of 140 miles per hour and gusts reaching 180 dN. The Labor Day hurricane of 1935, which killed hundreds in the Florida Keys, had winds so fierce that sand was blasted into building paint and wooden planks were hurled through palm trees like spears. If the Quonset hut collapsed in such a storm, the result would not just be property loss, it would mean lost lives and destroyed equipment. Brandenburger's team began by revisiting the basic physics of why arches work. When wind strikes a flat wall, it produces what engineers call a pressure coefficient. The wind pushes directly against the surface with full force, but a curved surface diverts the wind upward and around, reducing that pressure dramatically. It is like the difference between how water flows around a river rock versus crashing against a dam wall. The semicircular shape of the Quonset meant that hurricane-level winds would glide over the structure rather than trying to tear through it. The corrugations added a second layer of strength. The ridges running lengthwise gave the panels structural stiffness, much like how folding a sheet of paper makes it stronger than leaving it flat. Each ridge acted like a miniature I-beam, resisting bending forces that would otherwise buckle smooth metal. The mathematics became fascinating when they examined how loads were distributed across the arch. In a traditional rectangular building, the roof presses down on the walls press on the foundation, and the entire system relies on vertical load paths that must remain intact. A hurricane can rip the roof off because it is a separate piece resting atop the walls. The Quonset arch changed that entirely. It was a single continuous curve, with each panel sharing its load with the ones beside it. Engineers called this a compression ring, the same principle that allows stone bridges to stand for centuries without mortar. The outward thrust at the base, the ring stress that tries to spread the arch apart, was countered by the ground itself. Each Quonset panel was bolted to its neighbor using 3/4-inch steel bolts spaced 6 inches apart, forming what was essentially a 48-foot steel cable shaped into an arch. But theoretical strength meant nothing without real testing. The Navy therefore carried out a series of verification experiments that bordered on brutal. They built a full-scale Quonset at Davisville, Rhode Island, and equipped it with strain gauges, pressure sensors, and deflection meters. Then they waited for the first major nor'easter. On March 3rd, 1943, a storm arrived with winds of 75 miles per hour and heavy snow, perfect testing conditions. Instruments recorded that the structure flexed less than 2 inches at the crown and then returned to its original shape once the winds died down. The panel joints held firm. There were no leaks. The structure performed exactly as the calculations predicted, which was both thrilling and slightly unsettling, because it meant thousands of lives would soon depend on this design. Testing the tropical environment proved even more difficult than simulating wind loads. You could not reproduce years of jungle conditions inside a warehouse in Rhode Island. So the Navy shipped a test unit to the Panama Canal Zone, where humidity averaged 85% year-round, and temperatures rarely fell below 80 degrees. 6 months later, the reports came back. The galvanized panels showed minimal corrosion and no structural degradation. But there was a serious problem with internal condensation. When warm, humid air met the cooler steel surfaces at night. Water literally rained from the inside ceiling. The solution required adding louvered vents at both ends and along the roof ridge openings that allowed hot air to escape and created airflow without weakening the structure or reducing weather protection. These vents added $47 to the unit cost, but transformed the hut from a steel sauna into a space humans could actually live in under tropical heat. The final engineering challenge was the question of foundations. How do you anchor a 9,000-pound building to loose sand or coral without pouring concrete? The answer came from tent technology, scaled-up steel stakes driven into the ground, connected to the hut's base with adjustable tension cables for harder surfaces. The team designed a bolt pattern that allowed the hut to attach directly to wooden ties or perforated steel plates. The beauty of this system was its flexibility. The structure could shift slightly with the ground's movement without tearing itself apart. In June 1942, the War Production Board officially approved the Quonset hut for mass manufacturing. And what followed was the American industrial machine at its absolute peak. The Navy contracted 10 major steel manufacturers across the Midwest and Northeast companies that had been producing grain silos and water tanks just 6 months earlier and were now retooling to build shelters for the armed forces. The Strand Steel Corporation converted its entire Penrose facility outside Philadelphia to exclusive Quonset production. The George A. Fuller Construction Company took over an old automobile parts plant in Chicago. Great Lakes Steel dedicated 2 entire rolling mills to manufacturing corrugated roofing panels. By August, these factories were producing a total of 1,500 complete huts per week, and the number was still rising. The production process borrowed heavily from the logic of the automobile assembly line. Large rolls of steel were delivered by rail. Each coil was 4 feet wide and contained enough metal for 30 panels. Roll-forming machines shaped the flat steel into corrugations, spaced precisely at 67 inches apart. This process stiffened the steel, making it stronger than flat sheets of the same thickness. Next, the panels were sent through galvanizing tanks, where they were submerged in molten zinc at 850 degrees Fahrenheit. This zinc coating was not paint. It was a sacrificial metal bond that prevented corrosion before the underlying steel could rust. In the salt-laden Pacific air, galvanization meant the difference between a 5-year lifespan and 50. The process added another $112 to each hut's cost. But it was non-negotiable after field reports showed that uncoated steel could corrode completely within 8 months. Each complete hut kit was packed with extraordinary attention to transport logistics. 96 corrugated steel panels were stacked together like nested bowls, reducing the package height from 4 meters to just 38 centimeters. Prefabricated plywood bulkheads with pre-cut doors and windows were packed flat between the steel panels. All bolts, screws, and assembly hardware were sealed in a single wooden crate, accompanied by illustrated instructions designed even for crews with limited English proficiency. The entire hut kit fit onto a standard 12-meter flatbed rail car. This compact packing method was critical because every train bound for West Coast ports carried Quonset huts alongside ammunition, food, and vehicles. There was no space for inefficient cargo. The shipping choreography was intense. Trains departed daily from Philadelphia and Chicago, heading to San Francisco, San Diego, and Seattle, where Liberty ships and other cargo vessels waited at the docks. Longshoremen loaded the complete hut kits into ship holds using cranes originally built for tanks and artillery. A single Liberty ship could carry 200 Quonset huts, along with their assembly hardware enough to house 200 troops. The Warshipping Administration tracked every shipment manifest carefully, because these huts were more than just buildings. They were strategic assets. A hut shipped to Guadalcanal in September might serve as quarters for a bomber crew by October. The difference between a working aircraft and a crew sleeping in the mud, the assembly process at the destination was where the Quonset's genius truly shone. The Navy's construction battalions, known as the Seabees, developed standardized methods that turned shelter construction into a perfectly orchestrated routine. One 6-man team. 8 hours. One fully habitable hut. The process began with site preparation, clearing vegetation, leveling the ground, and laying gravel if available. 2 men handled the end walls while 4 others worked on the steel panels. The sheets overlapped by 6 inches and were bolted together with 3/4-inch fasteners. No welding, no concrete, no special skills, just wrenches, a level, and a willingness to follow illustrated diagrams. The record for speed was set on Espiritu Santo in January 1943, when a specially trained Seabee crew assembled a complete hut in 4 hours and 17 minutes. But that was only for demonstration. The real success lay in consistent, large-scale output across hundreds of islands, where crews built 5 or 6 huts per day, every day, constructing entire bases faster than the enemy could bomb them. By December 1940, monthly production had reached 8,000 units. The logistics network was so efficient that huts ordered in Pennsylvania arrived in New Guinea within 40 days, including transoceanic shipping and Pacific transport. The cost breakdown told the story of victory through efficiency. Each Quonset hut provided weather-resistant housing for 36 men at a material cost of $394 and roughly 60 man-hours of assembly. By comparison, a traditional wooden barracks required $12,000 in materials, 400 hours of skilled carpentry, and 6 weeks of construction time. The Quonset achieved shelter at 1/10 the cost and in 1/20th the time. By mid-1944, the U.S. military had deployed more than 160,000 units across every theater of the Wehrnuff housing for nearly 6 million personnel built in less than 2 years. Guadalcanal, August 1942. The first combat-deployed Quonset huts landed on the beaches, where temperatures hovered around 98 degrees Fahrenheit with 90% humidity, and Japanese bombers still made daily raids on anything resembling American infrastructure. Naval engineers unloaded the flat steel panels under sporadic artillery fire and began bolting them together in a coconut grove still scorched from the previous week's bombardment. Within 12 hours, Henderson Field had 10 new structures ready to serve as quarters for the weary maintenance crews of aging F-4F Wildcat aircraft. The true test came 3 days later, when a Japanese bombing run came dangerously close. A 225-kilogram bomb detonated just 36 meters from a hut filled with aircraft mechanics. The blast flattened nearby palm trees and shredded canvas tents like paper. But the Quonset hut flexed instead of failing. Dirt and shrapnel bounced off its corrugated steel skin, and when the smoke cleared, the building still stood, shaken but intact. With every man inside alive, the jungle proved to be as relentless an enemy as any opposing force. Within 2 weeks, red rust appeared on every bolt that was not galvanized. The salty air corroded standard hardware like acid. Mold grew on anything that stayed damp, turning the interiors into abstract canvases of black and green stains. The ventilation shutters that seemed adequate during tests in Rhode Island were nearly useless against the suffocating tropical air. Marines began propping doors open around the clock and cutting extra vent holes with tin snips, violating structural specifications but making the huts livable. These field modifications were recorded and sent back to Quonset Point, where engineers incorporated them into later production runs. Improved ventilation, larger shutters, and every single bolt-hot dip galvanized, regardless of its position. Iwo Jima, February 1940. The volcanic island presented a completely different kind of hell. Black sand blew into every crack. There was no solid ground for anchoring, and artillery from Mount Suribachi was a constant threat. Marines arrived on D+2 and began assembling Quonset huts under fire, literally bolting panels together while mortar shells landed 200 yards away. The volcanic sand made traditional staking impossible, so crews improvised by filling empty oil drums with sand and lashing them to the hut bases with cables. When a Pacific typhoon struck in March with winds reaching 177 kilometers per hour, those makeshift anchors held firm, while wooden structures across the island were torn apart. The base commander's report to Pearl Harbor was brief: the Quonsets survived. Everything else is gone. The Arctic environment tested the design from the opposite extreme. The Aleutian Islands campaign in Alaska saw Quonset huts deployed at Dutch Harbor and Adak, where temperatures plunged to 40 degrees below zero and winds regularly exceeded 100 miles per hour. The cold made steel brittle, and the first units developed cracks around the bolt holes. Engineers responded by specifying cold-rolled steel with a different metallurgical composition for Arctic deployments and adding rubber gaskets at every joint to preserve flexibility. Heating the huts brought its own problems. Warm air meeting frozen steel created condensation so severe that it literally rained indoors, until crews learned to install insulating blankets and keep the ventilation system running even in sub-zero weather. By the winter of 1943, weather-hardened Quonset models featured inner insulation layers, double-wall construction for extreme cold regions, and improved ventilation systems that prevented heat loss while controlling humidity. North Africa and Italy presented completely different challenges. In Palermo, Sicily, a Quonset hut used as a munitions depot took a direct hit from a German 88mm shell. The round pierced the steel skin and exploded inside among crates of small ammunition, a blast that should have vaporized the entire structure. Instead, the curved shape redirected the explosion outward through the walls and roof in a pattern that twisted the frame, but kept it standing. Explosive ordnance disposal teams inspecting the wreckage noted that a rectangular building would have collapsed completely, trapping anyone nearby under tons of debris. The inherent strength of the arch, the compression ring effect, meant that even catastrophic damage rarely caused total structural failure. The Pacific typhoon season of 1944 delivered the harshest endurance test of all. Typhoon Cobra struck the Philippines in December with winds reaching 225 kilometers per hour and waves up to 6 meters high. At Tacloban, the storm destroyed 80% of all base structures. Wooden buildings shattered into splinters. Concrete installations collapsed as wind erosion undermined their foundations. Yet of the 43 Quonset huts on the base, 39 remained intact, and the 4 damaged units were still repairable. Their panels bent and seams torn, but the structures held. Engineers studying the survivors found that proper anchoring mattered more than any other factor. Huts with solid ground connections withstood the storm. Those with weak or improvised anchors rolled away like tumbleweeds. By the end of the war, field performance data from 50 combat zones had been collected and used to refine the design continuously. The 1945 production models were almost unrecognizable compared to those from 1942, better ventilation, stronger fasteners, improved insulation, and field-tested modifications that turned a good design into an outstanding one. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Almost overnight, the United States Army found itself with roughly 170 Zeros Quonset huts spread across 6 continents and no clear plan for them. They had been conceived as wartime temporary shelters to be dismantled or abandoned once permanent bases were built. Yet no one wanted to throw them away. At hundreds of installations scheduled for closure or downsizing, commanders looked at their Quonsets and saw not wartime relics but sturdy, low-cost, ready-made buildings usable for almost any purpose. The War Assets Administration, charged with disposing of surplus military property, faced an odd problem. Public demand for used Quonsets far exceeded the available supply. Returning veterans encountered a housing shortage so severe that many families were living in converted chicken coops or sharing apartments with 3 other households. After 4 years of war, the construction industry was short of both materials and workers. Into this crisis stepped the Quonset hut, now offered to civilians at liquidation prices between $1,000 and $2,500 for a complete unit when a conventional house cost around $8,000 if a builder could even be found. Federal programs for veterans encouraged these purchases, turning the wartime hut into a peacetime lifeline. By the end of 1946, whole suburban communities built entirely of Quonsets were appearing around major cities. Roger Young Village in Los Angeles housed 750 families in converted military structures. Vetville neighborhoods sprang up near universities swelled by GI Bill students needing instant housing. Homeowners proved inventive. They added wooden facades to the curved ends, so the buildings looked like small cottages rather than military surplus. Inside, partitions created bedrooms, living rooms, and kitchens. Windows were cut into steel walls, technically a structural violation, but one that made family life practical. Some families buried half their huts for insulation, or linked several together to form larger homes. Housing inspectors and city officials were initially reluctant to approve such alterations, but the shortage was so dire that permits were granted out of necessity. In Portland, Oregon, an entire district known as Fairview Addition consisted of 350 Quonset houses. Residents planted gardens, painted their steel walls in bright colors, and built porches that disguised the structure's utilitarian origins. Churches soon saw another use for the design ready-made worship space for rapidly growing suburban congregations without decades-long fundraising campaigns. The First Presbyterian Church of Levittown, Pennsylvania, held services in a Quonset hut from 1952 to 1967, until a permanent sanctuary was finally built. Dozens of other parishes made the same choice. $500 for immediate space was better than $150,000 for grandeur years away. The acoustics were poor and the appearance plain, but people could gather to worship next month instead of next decade. Many of those temporary church huts remained in service for 30 years, outlasting the very generation that once saw them as stopgap shelters. Education saw a similar wave of adoption. Post-war enrollment surged as the baby boom began, and school districts faced the same challenge that had confronted the military back in 1942. They needed classrooms immediately, while traditional school construction took years to complete. Rural districts in particular favored the Quonset classroom. A small hut could hold 30 students at a cost barely 1/10 of a conventional school building. By 1950, an estimated 3,000 schools across the United States contained at least one Quonset-style classroom. Some children spent their entire elementary education inside these curved steel tunnels, learning multiplication tables and American history beneath ceilings that had once sheltered B-29 bomber crews over the Pacific. The commercial sector soon joined in. Small businesses, machine shops, auto repair garages, warehouses, and agricultural equipment storage facilities discovered that the Quonset hut provided open, unobstructed interior space ideal for industrial work. A welder could set up a workshop in a surplus hut for less than 2 months' rent of a typical commercial space. Agricultural use became especially popular. The original Strand Steel Corporation, which had helped design the Quonset for the military, returned to produce civilian versions marketed directly to farmers. Thousands of farms across the Midwest added Quonset structures to store grain, equipment, and livestock. Maintenance requirements were minimal, a quick wash of the exterior once a year, a periodic check of the bolts, and the structure could last indefinitely. This civilian embrace of the Quonset created an accidental architectural legacy. The huts became embedded in America's visual culture as symbols of practicality over luxury, function over form, and ingenuity born from necessity. They appeared in films, television shows, and photographs as shorthand for post-war optimism mixed with a touch of austerity. Architectural historians initially dismissed them as temporary eyesores, but by the 1990s, preservationists began recognizing surviving Quonsets as important examples of adaptive reuse and vernacular design. A number of huts have since earned historic landmark status, protected as enduring symbols of a unique moment when military technology successfully transformed into civilian life. Modern disaster zones tell us exactly why the DNA of the Quonset hut keeps reappearing in 21st century emergency response. When the 2010 earthquake devastated Port-au-Prince, Haiti, relief agencies faced the same challenge that military planners had confronted in 1942: immediate shelter for hundreds of thousands of displaced people with no existing infrastructure, no time for conventional construction, and conditions harsh enough to destroy most temporary housing within months. The solution that emerged was based directly on Quonset principles. Even if the designers did not realize they were reviving 1940s military engineering arched steel frames, corrugated panels, and prefabricated components that could be shipped flat and assembled quickly. The formula has endured because the physics and logistics that made it work 8 decades ago have not changed. The United Nations High Commissioner for Refugees now deploys temporary housing systems known as RHUs, or refugee housing units, which are essentially Quonset huts refined by 80 years of material science. Instead of corrugated steel, they use insulated composite panels. Instead of bolted assembly, they employ modular snap-fit connections. Yet the core concept remains the same: a curved profile for structural efficiency and wind resistance, a self-supporting arch that eliminates the need for internal framing, flat-pack shipping for mass delivery to remote locations, and assembly by unskilled workers using only basic tools. A 2-person team can erect a modern RHU in 4 hours, almost identical to the 1942 Quonset specifications. Today, more than 200,000 displaced people live in these shelters across refugee camps in Africa, the Middle East, and Asia. Storm-resistant construction has also rediscovered the strength of curved geometry after decades of rectangular buildings collapsing under hurricane winds. Following Hurricane Katrina's destruction of the Gulf Coast in 2005, engineers studying which structures survived found a clear pattern. Curved buildings consistently outperformed box-shaped ones. Along the Mississippi coast, entire neighborhoods of conventional houses were reduced to bare foundations, while a handful of Quonset-style metal buildings remained standing with only minor damage. This evidence inspired new research into what structural engineers now call aerodynamic architecture, designing buildings to work with the wind instead of fighting it through brute strength. The The resulting structures look remarkably similar to the Quonset hut, because physics has not changed. Wind flowing over a curve creates far less pressure than wind striking a flat wall, just as it did in 1942. Even the modern tiny house movement has unknowingly revived Quonset principles as designers seek to maximize interior space with minimal materials and cost. Several companies now produce prefabricated dome cabins using the same corrugated panels and self-supporting curves first pioneered by Otto Brandenburger. These cabins are marketed to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. Their advertising emphasizes sustainability and contemporary design, rarely mentioning that their architectural DNA traces back to a World War II military shelter. Some high-end architectural firms have elevated the aesthetic, creating luxury versions with floor-to-ceiling glass end walls and premium finishes costing up to $300 per square foot, while retaining the signature arch. The humble wartime dome has evolved from a symbol of necessity into a modern statement of design. Military applications never truly stopped. The United States Armed Forces continue to deploy dome-style shelters in conflict zones, Afghanistan, Iraq, and classified locations all feature modern versions of the original Quonset design. Current military specifications require units that can be airlifted by helicopter to mountain bases, assembled under combat conditions, and withstand explosive shockwaves. The materials have changed: aluminum alloy frames, Kevlar reinforced panels, integrated climate control systems. But if the engineers from Quonset Point in 1942 were shown a deployable military shelter from 2025, they would instantly recognize their own design philosophy. The newest innovation is the expandable version, which unfolds from a shipping container like origami and locks into rigid dome structures within an hour. The economic logic that justified Quonset construction in 1942 remains just as compelling today. When disasters strike or rapid deployment is needed, conventional construction simply cannot compete in speed or cost. A modern dome structure can provide weatherproof protection for about $50 per square foot, including transport and assembly. Conventional building at the same site, assuming contractors are even available, costs between $150 and $300 per square foot and takes months instead of days. For humanitarian organizations operating on donor-funded budgets or military logistics divisions managing trillion-dollar expenditures, that cost gap is critical. The same equation that drove the original Quonset program, how to shelter the greatest number of people for the least money in the shortest time, remains unchanged because the economics of scarcity have not changed. Perhaps the ultimate validation comes from space exploration, where NASA and private aerospace companies designing habitats for Mars have repeatedly arrived at Quonset-like solutions. Proposed Martian shelters use arched configurations to resist the planet's intense dust storms, prefabricated components compact enough for spacecraft transport, and self-supporting structures that require no deep foundations in the Martian regolith. The constraints of interplanetary construction, harsh environments, limited tools, unskilled assembly, and maximum strength from minimal material mirror almost exactly the challenges faced in the Pacific Theater of 1942. Independent engineers continue to rediscover the same solutions. When humanity finally builds permanent shelters on another planet, it is entirely possible those structures will carry the design legacy of 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and pure ingenuity.